Good evening and welcome to our STS-133 Flight Readiness Review briefing. We are happy to be here this evening and joined by NASA's Associate Administrator for Space Operations, Mr. Bill Gerstenmaier, Shuttle Launch Integration Manager, Mike Moses.
Good evening.
And Shuttle Launch Director, Mike Leinbach.
Good evening.
We'll begin with opening comments and then we'll be happy to take your questions. Mr. Gerstenmaier.
Thanks, Mike. We had a really thorough review today, and we set the 24th at 4:50 p.m. for the launch of Discovery. We had a good discussion about how all that goes with the ATV and its docking, and ATV is continuing to do very well on orbit. They did a collision avoidance maneuver checkout today, and that went extremely well. If things go as planned, about 6 hours before the launch, ATV will dock to ISS, and then we'll go ahead and then launch the shuttle right after that. We took a look at it from an overall timeline standpoint, make sure there were no conflicts with the on-orbit crew, make sure we could get all the testing worked out and fit in, and all that worked extremely well. It's also a pretty interesting time overall with the station, lots of activities going on. As we were in the FRR today, the HTV was moved from the Nadir port up to the Zenith port. That was important. That clears the way for the shuttle to come up and dock. The HTV needed to be moved, and that was done. The power cable was also attached, and I think the crew ingress is on Monday back into the HTV, and they'll be able to get in there to do some work. Sunday, progress on docks, so it's a busy time. We also spent a little bit of time in the flight readiness review and talked about the potential for a Soyuz fly around. We take some pictures of the station. We didn't approve that today, but we'll let the teams go ahead and continue to work it during the on-orbit activities to see if it makes sense. The Russians will continue to evaluate it. If it works out and works right, we'll get a decision around flight day 6 if we want to go do that activity. So we went over all the systems. We spent quite a bit of time talking about the external tank and the stringers to make sure we were comfortable with the modifications we've made to the tank, make sure we've got everything in a good configuration. I can't say enough about the work that the teams have done. They did a tremendous job down here at the Cape, removing the foam, installing the radius blocks, making the modifications, getting the orbiter back out at the pad. The team just did a tremendous job. And then the number of hours that were spent in various test facilities testing all the configurations of the stringers and the tank components to make sure they were really ready and we understood what was going on is just phenomenal. So we had a very thorough review, a very in-depth discussion on the tanks, and things are looking pretty good. We're also are working now on ET-122, and I think most of the modifications are completed on that tank, and we'll start getting it ready to go support the April 19th launch. So again, the teams have done a great job. I think we're ready to go next week, and we're ready for the launch. So Mike?
Thanks, Bill. So let's see, I can't even begin to echo enough what Bill said about the work of the teams around the country, led by our external tank folks with Lockheed Martin at the Michoud Assembly Facility just outside of New Orleans, and then at the Marshall Space Flight Center in Huntsville, Alabama. The amount of effort and work that went into this is really, truly amazing. And then you couple that it's at the end of the program and we're done building tanks, and we've effectively almost all but turned out the lights at that MAF facility. To have this type of failure come in that requires a whole lot of test and analysis is a real testament to the dedication and loyalty of those folks to step up and really come out and help us, including the teams that had to come out here to Kennedy to do the mods on the tank themselves. You know, we had folks come out right after the holidays and get started on the modifications to the tank. And then again, the local KSC team who had to go through a whole lot of work. We were looking at it from a work time issue to make sure we hadn't had too many people working too long. And you go all the way back to the November 5th launch attempt where we had the GUP leak. And that's that same mechanical team down here at Kennedy who works on the GUP as they work on the rest of the ET. So not only do we have to tear the GUP apart, fix that leak, put it back together, but we had to initially we did repairs on the tank out at the pad, and then decided we wanted to do a tanking test. So we added instrumentation, and then we recognized we needed to roll back, had to do a modification, and then roll back out. And when we got back out there, we hooked the GUP all back up again. So that team's been working really hard and have absolutely done an amazing job. I am very, very proud of them and the management team on top of that structure to make sure that those guys are getting what they need to get their job done. Really, really good job. We talked a little bit at FRR, since we were last had our flight readiness review, which was at the end of October. A couple of things technically we talked about. We had a circuit breaker problem that led to a power anomaly in one of the main engine controllers, and we had talked that and we were ready to fly with it as is, but since we had the downtime, we went ahead and changed out all those circuit breakers, 18 of them on one of the panels in the cockpit. So we have all new circuit breakers in that system and everything's good there. A lot of time and cycle stuff, batteries that needed to be changed out, components that have a clock on them when they need to be changed. We had to look at each one of them to say, does that really need to be changed right now, or was that requirement more from a more frequent use, and since we hadn't launched, we're okay. So we looked across the board at all the systems and had a handful of things that needed to be worked on, and the ground ops team here in Florida really led that effort and did a great job of keeping us on top of that list. And we kind of talk about it. I don't know if you've seen the videos where they how you pay attention to a problem. They show the team passing a basketball back and forth. You're supposed to count the number of times the basketball goes around, and then meanwhile a bear or a gorilla walks right through the middle of it, and you usually don't notice that because you're paying attention to the basketball. Well, the stringers were our basketball here, and everybody was paying attention to it. So the rest of the teams were really trying to focus on all the rest of the stuff to make sure we didn't miss anything, and we reviewed that pretty good today, and high confidence that we were in great shape on the rest of the vehicle. We swapped out the crew. Tim Copra got replaced by Steve Bowen. He's going to be doing the EVAs. There's 2 EVAs. He has completed all the training needed for that. He's gotten his NBL runs. He's gotten his VR lab runs and all the desktops that he needs to walk through the procedures there. Came right back up to speed, no real issues, and Tim was right there helping him learn the tasks. So we didn't really change any of the tasks on the EVAs. The only real change happened in the arm ops. Tim Copra was going to be the backup arm operator on one of the ELC and PMM moves, and then he was going to be prime on another. So rather than trying to get Steve Bowen trained in arm ops, we switched over. Now that we have the 25S crew up there with Paulo Nespoli, Katie Coleman, and Dmitry Kondratev, we're going to give them the tasks. So Katie's going to pick up some of those tasks. They've been trained for arm operations, so they'll pick up some of that. All in all, the crew was in really good shape and felt very, very comfortable with this crew change, and so no issues from a readiness standpoint there. And again, the mission baseline hasn't changed. We're still doing the PMM, the Permanent Logistics Module Install. That's the MPLM that we last flew on STS-131 that's been outfitted for permanent stay on station. We're still going to put the ELC, the External Cargo Platform, over that has a spare radiator and some empty cargo spots on it. We're going to do those 2 EVAs, clean up a lot of if you remember way back when we had that failed pump module on station, there's still a few tasks waiting for these EVAs to come clean up and put that pump module back where it stays until it's returned home on STS-135. That's all staying the same. The only real change is what Bill mentioned with the possibility of doing a Soyuz undock and fly about. It's kind of akin to a Soyuz relocate. We're going to go back out a little further than that to get a little bit wider angle shot. And again, we're going to kind of work that through our normal approval process for how mission changes come in and make sure all the right procedures and all the right analysis is done and be good to go. On the tank stringers, we spent most of the later half of the morning and most of the afternoon talking about it. There was, I'd characterize it as very good discussion and diving into all the details behind the data. Not any real dissent of anything. This just really came down to 2 different aspects. There's the failure mode and what caused it and how it occurred, and what we're really coming down to root cause or most probable root cause there is it's a stack up of small stuff. We learned that the way this part can be built, the assembly stresses that can be put into it can really kind of lock up some stress. If you think about it, this is a metal stringer that's being riveted to a metal skin, and it's intentionally bent up over this angled cord. And as it's riveted down, if the angles aren't exactly right and there's some gaps in there, you're going to kind of squeeze it together a little harder, and that kind of locks some stress into the part, such that when we go and put a cryo load on it and this whole thing wants to shrink and that load goes up, you've kind of taken away, or I should say, let's think of it the other way, you've added some extra load onto that wasn't really supposed to be there in the first place. We thought that was really going to be our problem right before Christmas. We kind of thought we had that root cause. We set up a whole bunch of tests and making these assembly glitches intentionally. We couldn't break the parts. We weren't able to break them. So we knew something wasn't quite right with that. And we went back and looked and kind of reopened the materials properties side of the house and recognized that that we had some unstable crack growth due to low fracture toughness in some of the parts we took off the tank, the failed parts we brought off the tank. And then we started looking at other parts. We had, this is ET-138. ET-139 was in component fashion ready to be assembled and become an external tank as you know it, with the oxygen tank, the hydrogen tank, and the inner tank bolted together. So all the inner tank panels were built, or at least mostly built for that system. So we had those parts to go look at as well. And we did some testing and found that back probably in about 2000 or 2002 timeframe, we had two different batches of material come in, the aluminum lithium material that's used to make these stringers, that had a heat treatment that didn't quite get what we needed to in terms of properties. This is one of those big picture lesson learned things that we're actually going to go right down and make sure as an agency we're going to grow from this. When we designed the super lightweight tank, we recognized that this is aluminum lithium was a very brittle material in the first place, and so we did a whole lot of math to show that if we had cracked stringers, structurally that tank would be okay. And when they did that fail-safe analysis, they found that you could have up to 3 of them in a row cracked, and you still had no problems with safety of the tank. That was looking at it from a structural perspective. So because of that, we didn't really put a requirement in the books for crack problems. So we didn't measure fracture toughness on the metal. We weren't really worried about it. We didn't recognize that a single crack would then lead to foam, could lead to foam being pushed out of place, which would then lead it to it liberating and become an integrated hazard and debris concern. So this is one of those, you can trace it all the way back to we didn't quite be as smart enough in the integrated analysis of a change as we should have been. And it's a theme that gets repeated a lot in human spaceflight, and it's a reason why we try to be as rigorous as we can. So we had some metal come in. We measure its ultimate strength, but we didn't put a maximum on that strength. And these two heat lots were at the maximum, the highest strength material we've ever got. You initially think that's a really good thing, but that also means that metal's even more brittle. The stronger it gets, the more brittle it gets. And so it had really low fracture toughness. And we found that scattered throughout ET-137, which is the tank we have right now, and even going back to ET-136 and then a couple of stringers on tanks as far back as ET-131 had this bad metal on it, this low fracture toughness metal. But we know low fracture toughness alone isn't enough to cause cracks, because after we tanked this tank, not every single stringer, I forget the numbers, there's probably close to 70 of them, 77 of them, that are this suspect metal. We only had 5 cracks. So we know fracture toughness alone also isn't the problem. So you have assembly stress that kind of adds residual stress into the parts, and then you have fracture toughness, which lowers the capability of that part. When those two lines cross, you crack a stringer. And so that's what happened to us. So this mod we put on really is just kind of, if you want to think of it, it's a big metal Band-Aid, and big is not the right word, it's about 6 inches long. We kind of added it on top of these rivets so that the stress is taken up and given some extra reinforcement in that location, and we don't have that problem when we hit that cryo loading shock on the oxidizer, the LO2 flange, which is at the top of the inner tank. We talked a lot about the hydrogen flange, and why doesn't that flange also exhibit the same type as it bends in? Why isn't it cracking? None of our x-rays to date have shown any cracks on that side. And what we learned was this assembly stress that happens on the LO2 side at the top of the stringer. When we lay this part up, you start at the bottom, which is the hydrogen side, and then you rivet from there up. And so any kind of misalignment, any kind of extra length, any kind of shims that aren't quite right, propagate themselves and manifest at the end of the stringer on the ox side, but they're locked in and controlled pretty well on the hydrogen side. So we're not seeing the assembly stresses on the hydrogen side. Even though those material properties are lower, there's just not enough stress in the system to make it break. So that said, we spent a lot of time being rigorous, as we needed to be, to go do the analysis and the tests to make sure that all that theory held up, that even with worst case dispersions, that we truly understood the system, and that hydrogen flange wouldn't break because we did not modify it, and that the modification we put on the top of the tank on the LO2 side wasn't going to do any harm. And all those results came back. It took us a while to get through all the data today. And again, we kind of talked about the actual number. Was the factor of safety 1.5 or 1.4 or 1.42? At the end of the day, we recognized that the ability to nail that number down exactly is just not going to happen. There's a lot of variables here, and we kind of bounded it by a risk assessment to say what are the likely failure modes, what are the likely causes, and we really kind of got very good agreement from the community and then our independent teams who were looking over our shoulder that we had a rigorous approach and they were happy with our analysis, and we ended up with a unanimous go to be ready to fly this tank. Now we're going to keep doing the math, we're going to keep working, we're going to keep testing. ET-122 is the next one up on STS-134. That tank was built way before this tank, so we know it didn't have metal coming from that heat lot, but the one thing we're missing there is metal sitting on the shelf at the plant that we can then go test and make sure that it really isn't a bad fracture toughness. Because like I said at the beginning, we weren't ever measuring fracture toughness. We don't think it is bad metal, but we can't prove it. In the time that we've been going on here, the teams think they have a good link and will be able to show us that metal is truly good metal and this is not a problem for ET-122. But we want to kind of back that up with some testing. And now that we get this flight behind us, we'll go do that before we fly the next tank. But we went ahead and added the modification to that tank just as a stopgap to say, let's be safe. We know that fixes the ox flange. ET-138 is our last tank flying on STS-135. It's a sister tank to ET-137 sitting out the pad right now. It will need the modification on the ox flange, and we're going to keep doing all the math to make sure we understand truly what's going on and see if we need to be a little smarter or we can understand the actual risk we're flying with on that tank. But at the end of the day, a really good summary of where we stand. We feel we have very high confidence. When you boil it down, we looked at what's going to happen if we're wrong and we do get a crack. The aero loads on this thing on the hydrogen side are such that most of those stringers are being pushed down by the aero loads, so you're not worried about foam liberation. And the size of foam that would come off would be kind of bounded by what potentially could be lost there from other mechanisms of foam loss. That's not saying that a foam loss from a cracked hydrogen stringer is okay, but we feel that the risk there is acceptable to us, and it's in that accepted risk category. We understand it, we know the likelihood of it, and it's very low, so we're good to fly. Let's see, what else? The big piece of that is kind of, we showed that if we're going to get cracks, we're going to be able to see them during tanking. There's plenty of time for the final inspection team to notice those. The camera crews that we have, the OTV cameras that are scanning the tank, we'll see this right away long before we lift off. And if we do see a crack on those flanges, we would obviously be no-go for that day. And we're not worried about lifting off. We just wanted to make sure that during ascent that load couldn't cause a crack or cause one to propagate and grow big enough to cause foam, and we showed that that was fairly well bounded as well and not a big risk to us. So there's a kind of a brief summary of what's been about 3 months worth of work, and really you've kind of heard interim reports from John Shannon as we've gone along that we still kept learning every single day, and we've just really turned the corner here in the last month where we think we finally bounded the problem. We pulled it all together today and showed that to the agency, and again got that unanimous consent that we're in a really good posture to fly. So with that, we're ready to move to the mission phase, turn it over to Mike and his team to get us launched and in orbit. You know, we talked a little bit about the range, and you know, you guys saw that we had that. There's no way we're going to launch on the 24th if ATV doesn't launch on their first attempt, and then they didn't, and we're ready to go on the 24th. And I've decided I'm not going to tell you guys about launch windows ever again, because no matter what, I'll somehow lie to you. But what happened is just like it happens every time. There's a lot of math that has to go into finding out whether it's a legal launch window or not. So you kind of take the first cut through. And when you get pushed into saying, hey, I need a little better answer, you go sharpen your pencil and you look at it. So we looked at the loads and the analysis, the thermal effects, and the power profiles, and found that you know, the generic ground rule that said you want 24-hour spacing between the docking and the launch of a vehicle to know it's okay. We decided here we're going to be okay. So the ATV is going to dock about 6 hours before we launch. We will have tanked the vehicle. If they run into a problem in docking, we will talk about that in real time. If it's a problem that looks like they can resolve and come back and fix in a few days, we'll stand down and scrub off for the day to let them have that chance to get docked. The station program really would like the ATV present for this mission. If it looks like it's a little bigger problem or something that needs a little more time to solve, we'll let the ATV move out to a parking orbit and we'll go ahead and launch the shuttle on time. We've talked about the mechanisms we're going to do, and that's all ready to pull the trigger on. So we're not going to talk about what it means if ATV can't dock. We still might launch that day. We might not. We'll have to talk about that one in real time. And that's really all I had. So Mike, you kind of, like I said, we want to focus now on flying rather than the analysis. So I'll let Mike lead us into that discussion.
Okay. Thanks, Mike. Well, from a processing perspective, we're in outstanding shape out at the launch pad. We're expecting to perform the final closeout of the aft compartment of the orbiter tomorrow. We got all that work done today and have powered down the ship now. So we're able to give the team a full 2 days off. We will come in Sunday afternoon and pressurize the COPVs, our high-pressure gas bottles on the ship. That's a hazardous task that we do late in the pad flow so that we expose a minimum amount of people to that hazard. And then that should go fine Sunday afternoon, Sunday evening, and Monday afternoon at 3 o'clock we'll pick up the countdown for STS-133. Meanwhile, over in the OPF, Endeavour is doing extremely well. Her OPF flow is essentially over. She's up on the orbiter transporter system, ready to roll over to the VAB, which will occur on the 28th of this month, and then out to the pad on the 10th of March for the April 19th launch. So everything's going extremely well on Endeavour too. I'd just like to take the opportunity to thank the 103 team, both locally and around the country, who as Mike said, paid attention to not just the 800-pound gorilla, but to everything else in the processing flow that has to go exactly right. We met every day, as we always do during an integrated flow, laid out all the additional tasks that we wanted to perform, and the team just responded in extremely great fashion. That all with all the distractions that are going on in the program right now. I'm very, very proud of the 103 team. So everything's going really, really well. Looking forward to the countdown starting Monday and a liftoff next Thursday. Thanks.
All right, Mike, thank you. We'll take questions first here in Florida. Bill Harwood.
Well, thanks. I've got a couple of questions, if I could. Bill Harwood, CBS News. For Mike Moses, I guess, realizing you don't have an exact factor of safety, I mean, obviously it's greater than 1, I'm assuming. And can you talk about where the relative risk lies for cracks? It's my understanding it's from the thermal shock of fueling that you have a better chance of making something happen than ascent loads. Could you explain the difference in that? And the second question I had was about docking the day the ATV, launching the day ATV gets there. Obviously, you're putting a cycle on the tank, and you're assuming that they're going to, I'm assuming that the risk of putting another cycle on this tank is outweighed by the need to get off on the 24th. I'm not sure I understand why it would make a difference if you just went on the 25th and let those guys get out of the way. So,
okay, well, let me handle the second one first. So back when we originally partnered these agreements with the ESA folks and ATV, at the time, we still weren't sure exactly what was happening on the range schedule down here in Florida as to what our actual capability would be. You know, we have, from a station shuttle program constraints standpoint, our launch window is from the 24th to about the 6th of March. When we sat down and looked at the range schedules, there's an Atlas launch and then a Delta launch also in that same 2-week period, and our landing was going to conflict with the Delta launch. And so we got approved for 24, 25, and 26 on the range, but we wouldn't have a whole lot more room than that before we run right into their launch with our landing. So when it looked like we only really had a 3-day window to launch, now we wanted to go back and say, hey, you know, we gave ATV 4 days to try, but we only have 3 for shuttle. This isn't working out so well. Let's see where we can push and squeeze. So we are getting squeezed a little bit. I would say that doesn't mean we're pressured to launch in the 24, 25, 26 timeframe. After the Atlas goes, we can come back on March 6th. And again, just like I kind of alluded to, we said March 6th was the cutoff, but that cutoff was because 24S was going to undock. The Soyuz was going to undock. We're doing all the work right now to let them undock to do this fly around. That work will allow us to let them undock and then go land. So we can stretch that launch window out probably to the 11th or so before we run into HTV trying to undock. So we have a lot of room at the back end of this window. It's just not a lot at the front. So if we want to maximize our opportunities, and again, with all the TDRS scheduling work, the Russian work, the ESA work, the Japanese work, our shuttle work, and then all the other work on the range, it'd be kind of nice to have it happen on the day you planned it rather than just constantly reworking it all. So we'd really like to try to keep the 24th if we can. So that's kind of what drove us to look at that. We still have 10 cycles left on the tank plus a launch, so there's no worry about using one up there. And if you look at the true risk to the ATV not docking, they're either going to have a problem in their rendezvous systems that you find out pretty much right away, or it's going to be a docking mechanism problem when you first get there. Neither of those two problems have shown up. They're using Russian pedigree hardware in the docking system. They're going to the SM aft port, which is a very well-known docking port. So the actual risk of them having a problem during docking that would make us need to bail out of that launch are extremely low. Like I said, from a planning and ground rules perspective, you try not to put yourself there if you can avoid it. But if it's something to do, as long as you look at what you're really doing, and we did in this case, it's not that big a deal. So that worked out pretty good for us. On the tank side, and from a factor of safety, when we're really at risk, kind of what made this problem hard is there's a set of fasteners, and really the way this works is the stringer comes up and then it kind of bends out a little bit as it goes across what we call a cord, and that cord is the big chunk of metal that then bolts to the oxygen tank, the liquid oxygen tank. As that liquid oxygen tank shrinks, it puts stress into these fasteners in this cord that are on the stringer, and each fastener sees a different load at different times. So the top couple see the highest load during that initial thermal shock when the liquid level passes over and this thing shrinks right up, and it kind of pulls and tears at those top couple fasteners. Once the LOX tank is fully loaded and you have the whole weight of that tank now pushing down on the inner tank, the next set of fasteners, 3, 4, 5, 6, 7, 8, start to see the highest load. So once you're fully loaded and then lifting off, they start to see the highest load. So at different times, we screen different fasteners. The fractography and the failure analysis showed that these cracks are starting up in the tops of the stringers. So we're confident that loading is a good screen, but it's not a proof screen for us. We can't. The analysis shows that it's not 100% screen to say all fasteners will be cleared, no cracks can occur after we've loaded the tank. Ascent still could cause a few cracks. So that's why we went ahead and put this radius block mod on there just to lock that down. So with this mod, we're not going to see cracks. We've added capability, almost doubled the capability and strength of these things based on all the testing we've done. And so we know that the ox side is in really good shape. On the hydrogen side, the analysis is we're not at a factor of safety of 1 because that would say that you're probably cracking. We know that we're not cracking because we've tanked twice, we've x-rayed. But again, we don't want to just rely on that small data set, so we did all the analysis. And that's where the fuzz on what the number really is starts to come in. Because it's not the normal way. When you normally compute a factor of safety, you're doing it from an analysis standpoint, and you're doing it as a design tool to then allow you margin to be wrong in that design. This is kind of a more test-derived factor of safety. In fact, it's probably not even fair to call it a factor of safety. The academics would probably cringe at us using it that way. But it's really more of a test-derived margin that you're able to show in the part. And that number is greater than 1. We have rules in the books to say what that number has to be when you're designing something, and that's kind of what happened. We could go back and forth as to are we meeting that rule or not. We know we're not because we're cracking. We shouldn't be cracking. So we know the design is a little deficient here, and it's not the design so much as it is the bad metal that's causing that problem. But rather than bicker about whether the number's 1.5, 1.4, we just kind of said, there's a cloud on that number, so we're going to accept that it's less than what's needed, and we're going to go lay out the risks and the reasons why we're okay to fly. I don't know if that's exactly answering your question, Bill, but
It is. Yeah, go ahead.
okay, fair enough.
Marcia Dunn?
Yes, Marcia Dunn, Associated Press, probably for Bill or Mike Moses. For the Soyuz fly-around, if it's done, is that simply for historic photography purposes, or is there some engineering technical aspect of it?
There's an engineering technical aspect. When we do the shuttle fly around, we get a chance to see the station kind of, if you look at it, we fly around this way. With this fly around, we're going to get a chance to see some portions of the truss in some areas that we've not seen before. So we'll get a chance from an engineering standpoint to capture some images of some areas that we have not looked at, which we would like to go look at. So there's that piece which we think is good. We also look at this as when the shuttle retires in the future, we're going to want to go ahead and continue to do fly arounds. We use that data a lot from the shuttle fly around to go look for micrometeoroid debris to the station. We also look for blankets that are degrading. We look for the radiator, that's popped up. So we use it as an engineering evaluation of the overall external health of the station. We're going to want to do the same thing when the shuttle retires with the Soyuz. So in a sense, this is preparation for that activity. It allows us to gain some experience of how we would do it with the Soyuz, how we would minimize the impact of the Soyuz departure to still get that fly-around kind of data. So we look at it as an engineering evaluation. And the way we've got it scheduled is it's kind of it's okay from a flight readiness review board standpoint, but it's really up to the team to see what happens. If we have to do a focused inspection or we have any other things that go wrong on the EVAs, we will not go do this Soyuz fly around. The Russians still have to review it. They've taken a cursory look at it. It looks okay from their standpoint, but they still have got to go give their formal blessing and agree to it. The crew's seen some of the procedures. They've looked at it, and if they don't like it, they'll wave off. So it's not a guarantee by any chance we'll go do this. But if everything comes out the right way, we'll go do this to capture the images, both from kind of a historical perspective, it's important because, you know, we will have the ATV there, the the European Automated Transfer Vehicle, the Japanese HTV. Progress will be there, Soyuz will be there, and the shuttle will be there. So it's a pretty unique period in the history of station with all these vehicles here to capture some images of that. So that has an aspect to it. But there's also this engineering aspect to capture some data of some areas we haven't seen before.
Thank you. And for Mike Kleinbach, I'm just wondering, since this is Discovery's last flight, has the past 4 months seemed to be sort of a reprieve for the team working on it and letting it be there longer for them to work on? And you mentioned the distractions. I'm just wondering how you expect that, if at all, to play out this year, in particular next week.
Well, I don't expect the distractions to come in at all. I mean, I've said before and repeat again today that when we get on console as a launch team, and the processing people out at the launch pad and in the orbiter processing facility and indeed elsewhere around the center, when they're on the job, they're 100% focused on that job. I don't worry about that a bit. The distractions come when they're off the job site itself, and then, you know, we talk about the future, and that's where some of the emotions kick in. When we're on console next Thursday, it will not be an issue at all. We'll be able to launch perfectly safely. We also have a process in place called the Shuttle Workforce Council, where we and management get together monthly, both on the NASA and the contractor side, and look system by system, the workforce levels, the experience of all the people in those systems, and can we safely support processing and launch. And right now we are green across the board. And so, yeah, there have been some layoffs, but we still have sufficient people here to perform the jobs perfectly safely, so no issue there. The reprieve, I don't know, it'd be, you like to open Christmas presents on December 25th, you know, maybe it'd be like opening Christmas presents a week late, I guess. I don't know. People enjoy the launch. We need to get on and do this, get Discovery on orbit, perform her last mission, and bring her home and get into transition and retirement. Reprieve, I don't know if that's the right word for it. People like to see it launch, the fruits of their labor, and that's what we'll get next Thursday.
Okay, we'll take a question from Todd Halverson, and then we'll go to the Johnson Space Center for questions.
Thanks. Todd Halverson of Florida Today for, I think, Mike Moses. Whenever you do modifications that are as extensive as what you've done with the external tank in this case, there always has to be a concern that you might introduce a hazard that goes unrecognized. I'm wondering, what about this situation right here makes you feel confident that this tank is safe to go fly?
Yeah, that's a good question. So we made the decision to modify this tank back in the early January timeframe, and we spent a lot of time before we made that go working on tests and analysis to show that very thing, that we would do no harm and that we would be okay. So on the surface, literally, you have to take the foam off and then reapply it. And so we looked at the amount of sprays that we required, how those foam bonds would go with each other. You know, the flange of the tank is one of the last things closed out, and it's a spray done automated at the assembly plant. And here we'd be doing it manually. We talked about the amount of material being sprayed, and it's in family with everything we've done here before in Florida. And what we did was the teams at Michoud basically practiced on test panels to develop the procedures they would use. We came down here, dry ran them, and then executed it. And so we kind of followed all our normal processes for how we repair foam. And so that gave us good confidence that we were able to take the foam off in the first place, because we know we can go put it back on safely. That's a little different than the hydrogen flange. It's one of the reasons we're not wanting to do anything to the hydrogen flange. The difference is the aux flange, it's at the bottom of the tank. So during ascent, there's always cryo there. It's always nice and cold on the backside. And so the temperature's kind of, it's got this nice cold back face on it. And so you're not worried about this cryo pumping loss where the little pockets of air liquidize, and then as you go up, they flash and push and pop the foam off the tank. On the hydrogen side, that's the top of the tank. So it's cold and liquid at the very beginning, but within the first couple minutes of ascent, that level's dropping in the tank. That now gets warm, and that heats up, and now you can have these cryo pumping effects. We learned that lesson pretty well during all the return to flight stuff for after Columbia. And so we are not confident that we'd be able to close that flange back out if we took foam off there in large quantities, because that's a very well-controlled, minimizes all the voids, and it's just not the same rigor that we could do here. It's not to say we couldn't. We just decided rapidly we didn't need to go there. So we wanted to make sure let's show that we can analyze our way out of the hydrogen side if we have to, and we did. So that's the foam part. So that was my first concern, is before we do anything, can I put it back together the right way? And then on the mod side, this mod's very much in family with other things they do to the tank. When they have damage, either the riveting tool kind of jumps off and smacks into the side of a stringer, or it gets handling damage, or a crack develops. This is the way they repair that. They pull it off. They put a doubler on. They put a radius block on. So it's a known process. The guys doing the work did it the same exact way they would have done it had this happened at the plant. We just now did it to every stringer instead of 3 or 4 stringers on every tank. And then lastly, we did all the math to show with actual test and analysis that it didn't actually do any harm. In all the tests we did to find the root cause, we then took all those runs and did them again with the mod on to show that it didn't cause the same problem again. So once we figured out how to recreate the failures in the lab, we then modified those just like we modified the tank and ran the tests again and showed ultimate capability was greatly improved. You back up to what makes me sleep good at night is the common sense part. You know, we're putting this little thin piece of aluminum Band-Aid on the part of the stringer that's wrapped up over a big, thick aluminum cord. So if you look at the total flexure of the system, we're basically adding a little tiny bit of aluminum on top of a big, thick piece of aluminum. So just common sense-wise, you look at that and you feel comfortable with it. That's a good thing, but it's also the bad thing, because that's when you stop to say, okay, now what am I missing? And I think we did all the homework there to show that we're not missing anything. We really are truly doing no harm on this one.
I think I'd add a little bit to what Mike said. We really tested this very rigorously. We actually changed the loading, because what you're worried about when you put a little piece in to stiffen an area, have you now transferred that load to another area that you didn't intend for that load to move to? So they did extensive testing where we looked at that from a visual standpoint. We got to watch a movie where you could actually watch the load get transferred to those other areas to make sure that there was not an adverse effect of that occurring. Then they actually changed the way they loaded, so they actually loaded the part in the area where there is no doubler or no little Band-Aid put on top of it to see what would happen if that occurred. And then they did extensive finite element analysis to go look at what this does from a math standpoint and compared the modification with and without the stringer. And then another piece, just to be even doubly sure, is that had limitations in the model. So the NESC is off running a different math model that will do exactly the same kind of thing to see if they can find something else. So this model that they ran had elastic, or that's where the metal yields but then returns back. We think it goes into the plastic region where it takes a set or stays in a bent configuration. The NESC model will look at that plastic configuration and see if that causes any problems. And we didn't consider that a constraint to flight, that work gets done because of the testing we've done. But they're off running that as well. So we were very cognizant that we could be doing something here that takes a situation that was bounded and creates a situation that we don't understand. So I would tell you the teams did a phenomenal job of doing this testing and pulling the work together. And I couldn't be prouder of what they've done, how they worked as a combined group from Marshall and Langley and JSC, and the MAF team came and pulled together and really did a phenomenal job. And to Mike's point, a lot of these folks, some of them in the tank world were laid off. They were already in other jobs, and we called them back to come back and do some of this work. And they were glad to come back, and they gave it their all to make this vehicle ready to go fly. So when I think about the spaceflight team, I think back of all those folks that I've seen at MAF and the folks that spent many hours, a lot of time over the holidays, over the Christmas time, over New Year's working this problem, and there was no question about their dedication to what they were doing. They really want to see this vehicle fly and help out Space Station and move forward.
Let's go to Johnson Space Center in Houston for a question.
Hi, this is Robert Perlman with CollectSpace.com with 2 questions, if I may. For Mike Moses, between November and now, has the ISS program requested any additional payloads to be added to the middeck to fixes for their systems or anything else?
Let's see. I think we might have put a new fluid jumper on board for one of the ESA modules, and other than that, I don't think there was anything. The only real change-outs were in regard to the crew swap to get the right size EMUs and gloves, and then personal gear on board for Steve Bowen.
Great. And for Bill Gerstenmaier, I'm just wondering if during the FRR today there was any discussion about the impact of the mission, if there was any, if on March 4th the government was unable to pass a new budget and there was a government furlough. Was there any talk about that today?
No, we didn't discuss that.
Okay, let's go to the phone bridge where I believe Denise Chow is standing by with a question.
Hi, thanks. Denise Chow at Space.com. With a question for Bill Gerstenmaier, you mentioned that it's sort of a unique time right now in the space station's history with all the international partners having vehicles present and docked there, and with Discovery bringing sort of the PMM, the last American edition. I was wondering if you could just comment on the significance of that.
Yeah, this is a pretty amazing time if you think about it. You know, if you look in the last month, you know, we've had the Japanese HTV launch from Tanegashima. We had a Progress vehicle launch from Russia. We've just had the ESA automated transfer vehicle launch from Kourou, French Guiana, and then we're going to have the shuttle launch here as well. So here we will have launches from the Kennedy Space Center, Kourou, Tanegashima, and Baikonur, all within a 1 month period. So you talk about a pretty amazing time of all these folks keeping track of all the activities that have to occur and keeping the space station operational. It's a pretty amazing time. And again, you should watch the video associated with this flight of the EVAs and step back for a minute and think about what we're really doing in space station. Look where the crew has to go all over this truss and what they are doing out on the outside of space station. I think maybe we take it for granted, but you need to step back and think about what's going on in space. To think about all these vehicles launching in 1 month from all these remote places, all these international control centers working together, this extremely choreographed 2 series of EVAs that are phenomenal across the truss. You think about space operations, this is probably the most intense space operations time ever in our history, and we just kind of take it for granted that it's just happening. But I think that the teams have done a phenomenal job of working things. You know, we were supposed to have a pallet to put the cargo on from HTV. It was supposed to be delivered by the shuttle. The shuttle didn't make it. So Dexter and the Spidum is holding 2 components waiting for the pallet to be delivered by the shuttle, and they'll get moved over to the proper pallet when the time comes. But that was not trivial for the teams to figure out how to move all that stuff around. As we talked about today, the HTV was moved from the port where it docked originally on the Nader, and it's now sitting up at the top on the Zenith, right? And I don't know how much that got covered. And we had to have a cable that was built on orbit installed because the cable we were going to use was stowed in the PMM on the shuttle, and it wasn't there. So the crew manufactured a cable to hook power up to the HTV on orbit. So this team is operating in an international, amazing system of operations and activities to just keep all the bits and pieces working and moving forward, and what a great team and what a great time in spaceflight.
Denise, did you have a follow-up question?
No, that's all. Thank you.
Okay, thank you. We're back here at Kennedy. We have about 5 minutes left in the briefing, and we'll go to Dan Billow.
Dan Billow, WESH-TV. I want to just ask you to elaborate a little bit more on the ATV docking versus the shuttle launch that day. I take it there's nothing that you're too concerned about that could be subtle, that could happen with an ATV docking that might manifest itself hours later or something like that. I mean, what protocol do you take to kind of make sure that the bases are covered and that, you know, what would trip the trigger to say we've got a problem, we can't launch or we can't dock?
Well, I could take a piece of that. You know, as the ATV approaches, you know, it's going to, today, for example, it did a practice collision avoidance maneuver, so we're testing all the thruster systems. We're testing the comm systems. So we will know pretty much in advance if there's something going on from an overall ATV standpoint. And so we'll know that ahead of time, probably even at the tanking meeting that Mike will chair, if there's any major problem that could be delaying the docking, and we can make a decision even before we start loading the tank. But when we're that close to docking, we will have checked out the majority of the systems on the ATV, and they'll be understood. It comes in and docks. It uses the Russian system to dock to the back part of the service module. It pretty much just bangs in and it attaches to the end. It becomes pretty obvious whether you're successful in docking or not. There's not a lot of mechanisms once it's attached. If it's not attached properly and it's in a soft dock configuration, then that's an obvious no-go. We would scrub out and not launch. If it hard docks, it'll be obvious to us right away. We want to do a little thruster test on the ATV, and we'll try to probably do that before the shuttle actually comes up and docks. I think we changed actually in the FRR. We talked about it one way. Then after the meeting, the teams thought about it some more, and they'll do a little thruster test. So there's very little risk of us not knowing whether this is successful or not when it occurs. It'll be pretty cut and dried whether we can launch or not. We'll have the right discussions, the right time to talk about it. And I would say it also, when we make the flight rules, we have to worry about crew sleep shifting. We have to worry about crew timelines. We have to worry about TDRS coverage. And to carry that in a generic sense, you really want that spacing. But then when you're into the actual mission specifics, you know the exact conditions of where the satellites are, the actual crew sleep shift time frames, all these activities, and then you can go look and say, hey, in this unique situation, does it make sense to go do this? So we see it as a good kind of risk decision that we would like to get 3 opportunities for the shuttle to launch. This gives us the first one, and we see that the chances of us having a problem with ATV low enough that it makes sense to move forward. And if we do, we can react to it, and it's an extra cycle on the tank, and we're where we need to be.
Okay, we'll take one question from Bill Harwood and wrap up with Marcia Dunn.
A very quick one for Mike. You guys had some problems with the GUP when you were hooking it back up after rollout, and I guess you swapped out a seal. Are you confident that when you guys, obviously you're confident, but given the vagaries of that system, why are you confident?
Yeah, so what we learned after the scrub back on November 5th, well, let me back up even further that. So after the first set of GUP scrubs we had on 2 different missions, we learned that we call it concentricity, which is kind of the alignment of the plate on the tank itself with the ground carrier plate that we bolt to that here at Kennedy, and making sure they're properly aligned with each other and that the holes in each of them line up so that there's a nice straight hole through. We learned that alignment was pretty key, and so we changed our processes to check it, measure it, and make sure we tweaked it just right. Then we had the scrub for the leak here on this one, and we learned that the QD that we plug into that hole has a bellows spring inside it and a little bullnose and a probe, and that can have an alignment within the QD itself, which can then cause that concentricity to either move to one side or the other. So what might look like a nice sweet spot down the middle alignment, when you hook this QD up, it kind of bends it a little bit and now pushes it down towards the limits where you might open up and gap and leak, and that's what happened. So we learned, if I want to be pretty crude about it, we learned the second piece of the puzzle that we didn't know about the first time we had the leak. So it took 2 failures to make us see both halves of the puzzle, and so now we did a whole extensive review, and now we truly do believe we have the whole complete picture. And that we can line this up properly every single time. We do now a whole lot of optics measurements on all the parts ahead of time, match them all up to say, with the alignments we see on the tank and the alignments we see in the disconnect, what's the right combination of parts to give you the alignment right down the middle. And then we did a bunch of offline testing to show that all the movement and the twang and the vent arm hooking up and pulling around won't move that alignment. Once you get if you can get it good and solid to begin with, it'll stay there. And so we have very high confidence that we have a good seal. When we got out to the pad, we hooked it up. We went back and did some data reviews, and there were some things there that caused us to question it. We've since done the math to show that we didn't move anything, and that was a perfectly good aligned system. But there was a little bit of question there, and we knew by going back to the new procedures and processes, we could remove some of that uncertainty. So we chose to redo it and just basically start back at square one again. And so I'm highly confident. We kind of gave it a 99.9% chance heading into the tanking test, and that was our proof in the pudding. We followed the exact same process and procedure to hook it back up again. So I expect the exact same result, that we'll have a nice tight system.
Marcia.
Marcia Dunn, Associated Press for either Bill or Mike Moses. Regarding Tim Copra, did you manage to get his own food preferences and his own clothes on board, or I'm sorry, are they still on board, or did you get Steve Bowen's stuff on board, and is Tim Copra coming for the launch, do you know?
I don't know if Copra's coming for the launch. We did swap out all the preference equipment. I think on the food question, if I looked at the exact math, I think Steve chose to keep some of the same menu items, so I'm not sure we changed out a whole lot of menu items. But yeah, he certainly had input. We had plenty of time to take care of that.
Yeah, and one other thing this evening at 7:23, if you go outside at 66 degrees above the southwest, you'll get a chance to see Station fly over the Kennedy Space Center tonight. So we ought to go do that here in a couple minutes. And then if you happen to be in Houston on Saturday, you get a special treat. At 6:47, you get to see the space station fly over, and then at 6:52 on Saturday night, you'll get a chance to see ATV chasing the space station and catching up. So the folks in Houston get a treat. I checked here in Florida, and it doesn't happen here, but the guys in Florida get a chance to go see both the ATV and the HTV. So it's neat for us to actually go see our hardware in orbit and actually see it flying overhead. You know, sometimes we see all the view graphs in the meetings and we're not sure it's real. So it's even nice for us to go outside occasionally and make sure that it's really there and it's doing what all those guys told us in these meetings. So that's our confirmation to show that orbital mechanics really works. So you should do that tonight at 7:23.
All right, and with that, we will wrap it up. Our next televised event for STS-133 will be the arrival of the flight crew on Sunday at 3:45 p.m. Eastern Time here at Kennedy Space Center. Once again, our launch is set for Thursday, February 24th at 4:50 p.m. Eastern Time, and you can keep up with all of the activities on the mission at www.nasa.gov/shuttle. Thank you very much.